Hey guys, welcome to PyData. I haven't been here before, so this is kind of weird for me. I've never seen this many coding people with this much social, walking around in forever. I'm kind of scared. I'm not a data scientist. I'm an astrophysics PhD student, but I really wanted to come. And I wanted to come because I need your help with my thesis, essentially. Be open about it. I need your open source libraries, I need your techniques, I need your advice. And that's because astrophysics has a problem. We're told in school that scientists form a hypothesis, they gather some data, they find some results, they come to a conclusion. In reality, astrophysics is drowning in a fire hose of data. Thanks largely to better telescopes, the amount of data we have is, frankly, it's insane. There's a radio telescope being built right now that will generate a petabyte of data per second. And that's 10 times more data than the entire internet traffic of the world. So we have some data problems. When you're talking about big data, you're talking about astrophysics. There's more to it, though, than just the amount of bytes. Sometimes it's also about the number of eyes you can put on data. So a little bit of science. In the early universe, you have dark matter, you have hot gas. And the hot gas condenses, it's attracted by the dark matter, and it forms the first galaxies, the first stars, and so on. And for nearly a century, astronomers have been trying to work out, how exactly does this process work? And one of the ways to do that is to divide galaxies into types. So here's some of the types. So you'll have elliptical galaxies, galaxies with sort of disk structures, spiral arms. You can have galaxies that have undergone kind of mergers and collisions. I'm making the cameraman work, sorry. That have sort of mergers and collisions. You can kind of see, if you look closely, if you're near the front, sort of two remnant cores, so two galaxies that are like halfway through merging into one galaxy. And that's sort of how we think the universe forms, this kind of hierarchical accretion of galaxies. But the devil is in the detail. We're trying to work out quite how that happens. Here's the catch. A single modern telescope can detect easily, say, 1 million galaxies. And there's telescopes in the next generation, 2020 or so, you'll be hitting billions. Our instruments have outrun our eyes. So most of the data they collect will never be looked at by any human being. And that's the first time that's true. So let's get more eyes. So welcome to the Zooniverse. This is the project that I'm part of. It's a website for crowdsourcing scientific labels. Sort of like Mechanical Turk for science, if you like. Researchers upload the subjects they need labeled, and hundreds of thousands of volunteers respond. Volunteers are transcribing the personal notes of the US Supreme Court. They are counting penguin populations in Antarctica, like literally penguin by penguin. Kids really love that, incidentally. It's a great way to distract your kids if you want to just have some peace and quiet. And of course, they label galaxy shapes. All the data we collect is open. Anybody can upload subjects, but it has to be for scientific research. And you cannot make money from the hard work of our volunteers. So this is not a pitch. You can't pay to join. I'm not selling something. Because we're not trying to make money, we're kind of happy to talk about how it works in a way that some of these commercial sites aren't. So I want to share with you a few stories of how our research teams have been dealing with some analysis problems that I think you might also face, or at least be interested by. All or nearly all of our analysis is done in Python. I think I can say on behalf of the science teams, by the way, how grateful we are for the PyData stack. Like, thank you. We literally couldn't do our jobs without it. So, NumFOCUS people, PyData, AstroPy, saved my life. Thank you, guys. The first challenge I want to talk about is getting good labels. So, we think a lot about data pipelines, statistics, machine learning. How often do we think about the people who do the labeling that goes into our models? And it's really important because garbage in, garbage out. If you don't have good labels, your whole job is going to be much, much harder. So here's a question. If I have a subject with many labels from many different people that disagree, how do I estimate the one true label? So if I want to build a model, I only need one value, but I have several votes. The Space Warps team had that problem. So a little science detour again. Gravitational lensing. Gravitational lensing happens when you have a massive galaxy that warps space around it and a galaxy much more distant behind it. And the light from the distant galaxy gets bent around the forward galaxy And you get these sort of effects. So here we have the foreground galaxy, this kind of red elliptical one, and in the background, these blue stripes. This is actually a galaxy twice as far away, directly behind, almost, the elliptical galaxy, where space-time is bending the light, almost like kind of a magnifying glass towards us. And it lets us see galaxies that we otherwise would never be able to detect. And instantly, you do the same thing with a wine glass. I want to show it to your kids or something. It's kind of cool. And that's really what's happening, but instead of glass, it's gravity. They're usually quite difficult to spot. So this is a really obvious image, but they're not usually this obvious. And volunteers generally disagree about whether an image is a lensed galaxy or not. And the scientists had to deal with that, those conflicting opinions. Here's what they did. So they simulated some fake lenses, and they uploaded them as well. Now, let's say I'm a user on the website. I'd be looking through images, some of which are simulations with no labels. And as I respond to simulated images, the answers I give are recorded and used to build a sort of a personal confusion matrix for me. So we're treating the users like classifiers, kind of the same way that we do usually. From a Bayesian perspective, a confusion matrix is the probability of an observation given a model. So the probability that I would say lens, given that it really is a lens, for example. So that's why I've written it maybe more formally than you'd be used to. And that means you can use Bayes' rule to combine classifications from arbitrarily many people if you know their confusion matrices, which you infer using the simulated data that the scientists have added. So we start with a prior. Lenses are rare, 10 to the minus 4-ish, so 1 in every 4,300 images-ish will be a gravitational lens, and you can work it out just from geometry. When a user classifies an image, we'll update our belief in what we think that image is, using Bayes' rule and using the confusion matrix that we measure. And as classifications come in, hopefully our beliefs will converge to one side or the other. So it's a log scale. You can see what's happening is the blue subjects, they're galaxies which we know do have lenses because they're fake. We simulated them. And the red is galaxies that we know do not. We've had experts look through a small number to have kind of a golden test set. And we can watch, as our beliefs are updated, as more classifications come in, they separate. So what we're doing is we're taking the conflicting opinions of different volunteers, measuring how well they perform, what they're confused by, and we're updating in a principled Bayesian way what we think the best estimate of the true label is. And once we're sufficiently confident, we'll retire the subject. We'll say, good, we're done. We have a label for that. We can move on. That lets us be a kind of Bayesian big brother. So now we know all the confusion matrices for our volunteers. We can kind of see how people behave. This plot shows the diagonal elements on the confusion matrix. So if you have the probability that I say it's a lens, given that it is a lens, and the probability that I say it's not a lens, given that it's not a lens. The line through the middle is sort of random. Each point is a volunteer. There's like a random sample of 200 or so. Happily, GDPR, I'm allowed to do this. I don't tell you any personal, but it could have been complicated. The yellow dots represent how many images a volunteer has seen. And you can see, first of all, there's quite a lot of variation. So people find this difficult, and people find it difficult in different ways. It's not clear that people are always positively biased, say. That's not really true. Which means that this kind of modeling approach is quite important to get good labels. But the reassuring thing is that there's kind of a drift to getting it right. People are hopefully learning. The more images you see, the bigger the yellow dot, the more astute you are, the more you're getting your large diagonal elements. So that means people using the website really are learning how to classify gravitational lenses in scientific data, and I think that's kind of cool. On the whole, people are improving, and giving us good labels means the scientists can do spectroscopy on these lens galaxies. Once they're published, they can follow up and they can try and find out what are they made of, how do they come to be. So, supporting science. But the Bayesian method kind of relies on you knowing some true labels to begin with, and that's not always the case. It also requires you to be able to construct a confusion matrix, also not always true. So for me, I'm technical lead of the Galaxy Zoo project, where we're classifying shapes of galaxies. And across all the questions, there's about 140 possible responses. It's kind of a decision tree we lead people down. And it's not easy to turn that into a confusion matrix. And if we did, it would be super sparse. We wouldn't get enough data to say how each user behaved on all of those elements. It'd be very stochastic. We had to try something else. So what we do, and this isn't something I came up with, it's something other smarter people came up with, is to reward consistency. So if I generally agree with the crowd, then I'm doing a pretty good job. Now, crowds can get things wrong, as we've seen in certain recent electoral moments. But on the whole, it is a very good way of discounting bad actors. So the way it works is you calculate your crowd predictions naively. Everybody weighted the same. You measure how often one particular person agrees. And if they agree with the crowd, then upweight them. And if they don't, downweight them and repeat. And you kind of iteratively converge on a consensus, where hopefully people who consistently disagree are automatically removed. Turns out that's kind of useful. So we give volunteers the option of selecting artifact, which skips the next image. We work with real data, so sometimes the images are genuinely bad, maybe a cosmic ray hit your telescope detector, stuff like that. However, people are not as well behaved as scikit-learn. In fact, sometimes I wish I could submit pull requests to certain people. I'm working on that. Here's what our consistently measure shows. So this plot is by Dr. Stephen Bamford. Each dot is a person. There's maybe 50,000 people on this plot, if you look closely. On the y-axis is how consistent they are with other people. On the x-axis is the total number of classifications they've done. And you can see there's kind of two distributions. So for most people, the more classifications you do, the more consistent you become. So we hopefully infer to mean that means people are learning. They tend to agree with each other more. However, there are these fun guys. No matter how many classifications they do, they don't become any more consistent. In fact, arguably they become less consistent. And this is a log scale. So this dude, has done 10,000 classifications. And he's almost the worst guy. And it turns out if you color by consistency, they clearly separate. And this is how often, if you color by how often they press the artifact button. In other words, the skip button. So what these guys are really doing is they're flicking through the pretty images. And they don't really care that they're messing up our data. They just want to see pretty galaxies. So that's the kind of stuff you have to deal with real people, sadly. The world is a little messy. But the consistency deals with that pretty well, and they're automatically downweighted. Yeah?
Do you offer feedback like, oh, you did the last 100 incorrectly?
Yeah. Please, you kick people off eventually.
But do you guys, does your platform offer feedback to these people? Okay.
So it depends which project. So the Galaxies platform doesn't yet. I joined about 6 months ago. That's something I really want to implement. But some projects do. The one I showed previously, the one with simulated gravitational lenses, they had kind of a training phase where they'd show you a very high proportion of simulated lenses, and they'd give you feedback on if you got it right or not. And then as you became more capable, they'd show you less simulated ones, and they kind of trust that you were doing a good job. They'd already have some estimate of your confusion matrix, and they just check in every now and again. So yeah, we do feedback, and it's really useful.
Can you see the images without volunteering? I mean, these tourists, so to speak, can they just go and look at them without?
Absolutely. I'll give you a website on Twitter later. You can just view the whole. All the data we use is from, a lot of it is from open telescopes. They'll have download services you guys can use as data professionals, but maybe just to view the sky. It's kind of fun. I'll send it around on Slack or something. It's a good point. So that was kind of a couple of things we found useful for getting good labels. You treat each person as a classifier with a confusion matrix and update your belief. Or if you can't frame the problem that way, then at least you can consider their consistency. Get rid of that guy, basically. That's how Galaxies currently creates labels. Now, this is a data science conference. You all know where this talk is going. We have a large set of data, most of which is labeled, but a lot of which is not. What are we going to do? Yeah, we're going to build a machine learning model. But it's not some Kaggle challenge. I need to do this to finish my thesis. This is important, guys. So I joined Galaxies earlier this year, and my supervisor, Chris, told me, here's 250,000 galaxies. I need them classified. When you've done those, 250,000 more waiting, And by the way, this should be a fairly short project. There's other things to do. It should give you about a year. So I did the math when I started. And this is how fast we're getting through Galaxies currently. And this is how fast we need to be getting through Galaxies currently, on average, by 2019, in order to be on track for my thesis. So I really need to build this thing. That's the good part. The bad news, yeah, when I said astrophysics has a problem, by the way, I meant that I have a problem. The bad news is this part. So there's a telescope called LSST being built. It will image an order of magnitude more than anybody else has ever imaged of galaxies. And my job is to deal with that data through our website. And for that to work, this is how well we need to be doing. So some work to be done. So this is why I need your help. I wasn't kidding. So I have a bit of a problem here. We're going to do a bit of, well, not really math, but a little detail now. This is the first sort of deep learning-y talk. And I noticed on the schedule that Sunday's pretty packed with them. I think you might hear deep learning once or twice more in this conference. We'll see. So I'm going to just spend a minute recapping how the method I use works, convolutional neural networks. It's a really good kind of become the de facto algorithm for analyzing images. And although you can use a lot of simple packages like Keras, PyTorch, maybe more fiddly TensorFlow to deal with this stuff, it's good to know how it works, even if you almost don't have to anymore. So I'll just recap it quickly. So we have an image, we want to classify it. We're going to pass over that image a set of matrices. We'll convolve with it, called filters. And the elements in those matrices will be the weights of a neural network. And they'll be shared across a layer. And that's what makes it sort of convolutional. All the weights in one layer need to be the same. If you do that several times, what happens is with each convolution, you will highlight certain features, say edges. And as you repeat it, you'll be building up an increasingly abstract feature map of what is in the image. So as opposed to, say, a random forest where you start with a set of columns, you have well-defined features. In images, you're trying to learn the best features. And if you change the scale of your convolution, in practice, you really shrink the sort of post-convolved image each time before you feed it into the next step, then you'll be increasing the scale that you're picking features out. So if you're first finding edges and things in small regions, and as you build up, you'll find, say, a spiral arm across half the image. So the convolutional layers are kind of like your visual cortex. They're sort of telling you what is in the world. And you can list off those features and put it into fully connected layers. The fully connected layers are more about your intelligent perception. Like, given what I know I'm seeing, a bunch of people in a room, what does that mean? And you hope that the output from that will correspond to a good prediction for what type of galaxy is this. Is it a spiral galaxy, is it elliptical, and so on. The reason that all of it works, the reason, the way we're going to set all of the three parameters, all these weights and biases all throughout the network, is by showing the network an image, measuring how wrong we are according to some cost function, and then slowly, iteratively changing those weights so we would have been less wrong, and repeat. And we hope that the weights and biases we learn will generalize so that when we show it a new image, our prediction will be better. And that's really what training is, and when people talk about backpropagation and gradient descent, that's what's going on. Backpropagation is just a mathematical trick to start from the answer and work back to what each of the weights should be without having to do too many second derivatives. That's really all it is. I want to tell you one other thing first, before we get back into it. So you've probably heard of dropout. So dropout is where you remove temporarily a random set of neurons from the fully connected layers, usually. And you require that you still have a good prediction at the end. So this happens during training. There's two ways of thinking about it. Either you're trying to reduce the dependence on any one particular neuron, so you still get good predictions, you're not too sensitive to a change in the weights or bias of that neuron. Or seen another way, you're training many neural networks, and you're kind of model averaging them. So it's like decision trees to random forests. If you have slightly varied classifiers and you take some ensemble, you generally do better. So that's kind of another way of seeing it. And that idea that we're training several models is going to be useful later. So that's the scaling science intro. I don't want to go. So the way the rest of this talk could be is this is how this is how we now use deep learning. We have better predictions. Look how well we do at classifying galaxies. I could do that. I think it wouldn't be the most interesting talk, and I think it wouldn't be the most interesting thesis. So I'm going to kind of jump to the next level for a bit. You can kind of trust me that we have a model that works, and I'm going to say, okay, what can we do with that that's cooler than just predicting some galaxies? Let's go one step further. What happens if we can close the loop? So if we have good labels, we can hopefully get a good model. But if we have a good model, can we use that to help humans give us better labels? Can we have sort of a machine to assist how the website works? Can we have a way to, the first example I'll give is a way to kind of ensemble the machine predictions and the human ones. So before we treated humans as classifiers in one way, now we really are using them as classifiers. We're going to try and combine to do better. So here's one cool example by Darrell Wright at Minnesota. So these are pictures of what we call transient events, things in the sky that change rapidly. Galaxies are basically static forever. They've been around for billions of years. They will be for billions more. And although they collide and so on, nobody would ever live long enough to notice, really. We only catch these things as snapshots. But lots of things in the sky do change. And this project was looking for supernovae, which are interesting to scientists to understand, particularly distance scales. You want to measure how far away something is. A supernova is a good way to do it because particular types are always the same brightness. And if you know how bright something is, you can infer how far away it is. So that's why it's kind of useful. So we have this project by Darrell where you show different images of the sky over time. One of these is a residual, kind of to help people find the difference, and ask, does it look like a supernova? And Darrell did something quite clever, I think. So he had his labels from the volunteers and kind of put them aside. And separately, he gave his data set to experts. And he had the experts also classify some different data, same images but split, and train a convolutional neural network like I showed you. So you have an expert-trained model and the human labels. And it turns out what you can do, so this is kind of a visual way of ensembling. Obviously there's smarter ways, but just as a straight-up way to show it in a presentation, you can separate your data much better if you have your expert classifier and your human labels kind of working together. So if this is the expert model, we only show stuff to humans that are beyond about 0.3-ish, just to save people's time. You can see if you wanted to separate out the real supernova, the red dots, then you've kind of done okay, just using the x-axis. But when we add in the human labels, you can do a much better job of kind of separating out this space if you do a cut like this, something like that, right? So just as a graphical way of showing it, the humans and the expert-trained model can kind of outperform either one alone. If you were to just take human labels and just train a model and then just use those predictions, you would do worse than this method. So I thought that was kind of clever. So astrophysics has a problem. I have a problem. My problem is to do with how do I show people the best images. So if I only have a certain amount of volunteer time, but I have many more galaxies than they could ever look at, I'm going to build a machine learning model, but I want to give it the best possible training data, and I only want volunteers to look at, therefore, the most useful galaxies to my model. I want to select the best galaxies to get labels for. And it's kind of a common problem. Anytime getting labels is expensive, and getting labels is always expensive in some sense, in time, in cost, the number of people you have to hire, whatever. Here's kind of a nice way of doing it. It's called active learning. Not something I came up with. Been around for ages, but surprisingly not talked about that much. if you have a machine learning model, let's say it's untrained or it's been pre-trained on some large data set that you have for a separate problem, you're going to do transfer learning, something like that. If you're going to make predictions on all of your subjects, and if your model is uncertain, take the most uncertain objects and send those to be classified. So in my case, I would put them on the Zooniverse on the Galaxies Zoo project, and I would have volunteers look at them. So I'd say, classify these 1,000 images on which the model is most uncertain. And I get labels back a few days later, and then add them to my pile of training subjects, retrain the model, and repredict, again, the most uncertain ones. So we're trying to select those images which most help the model. The hard part for me is finding out what would mean by uncertain. So if you have, say, a binary classification problem, that's kind of trivial, right? P equals 0.5 is the most uncertain things. Really, I have kind of a regression problem. I want to say what is the vote fraction, the number of volunteers out of all the volunteers who would give this answer? So everything is really in the continuous limit. And I want to keep that aspect because some galaxies really are ambiguous. Some people really do disagree. Our images are only so good and features can be unclear. We might genuinely not know, but when scientists come to use it later, it's an important distinction to keep because you can imagine a scientist making kind of a bootstrapping effect. If I want to say, okay, do galaxies with spiral arms look bluer? It matters which galaxies have spiral arms. And if I know the confidence well, if I know that vote fraction well, then I can sample and get an uncertainty measurement on my color versus spiralness relation. So that will help people to preserve, but it's tricky. So the way we do that, or the way we hope to do that, is with Bayesian neural networks. So the reason I talked about dropout before, and the idea of it being training many models, is going to kind of connect with the idea, if you're familiar with kind of variational autoencoders, the idea that you're trying to estimate an uncertainty. It turns out that doing many forward passes at test time, instead of when we're as well as when we're training, but also when we're testing on an image to get a real prediction out, is in the continuous limit equivalent to a Gaussian process, for the people who know what that is in the room. It's like training many models and seeing how much their predictions will vary, and using that to get some confidence limit on what our prediction will be. So we kind of hop between, do this a few times on a forward pass at test time, and see what's the confidence of my prediction. And if you were to take those forward passes and put it more in the sort of statistical language of sort of Gaussian processes, we're kind of assigning a distribution to each of the weights in the network. Instead of having a single scalar or a set of scalar weights, every weight is really characterized by some distribution now, and therefore so is my answer. So that's going to give us more of an idea about if things were slightly different, what would we say about the image? So I'm hoping to use that to pick the most uncertain images in a more sort of principled way, and in a way that I think is a bit novel. We'll see if it works. Come back to the conference next year and we'll find out. This has kind of gotten to the point that, this is literally what I'm going to go back to my computer and work on. We'll see. I think it's kind of neat. And I think it's kind of cool to see how the techniques that we're developing are sort of coming full circle, where we can have human-in-the-loop training. So it's kind of different to work in a Jupyter notebook and build models as to work in a production system where you have tens, even hundreds of thousands of people and some control over what you ask them to do. So humans, I think, in the future will become more of a part of the way we do machine learning and the way we build models. And I think that that's probably a good thing, but I think that there are important things for us to think about when that happens. I want to show you, this is the splash screen of a major commercial crowdsourcing website, which I won't name for legal reasons, but I might have mentioned it earlier, so maybe you can infer it. They say human intelligence through an API, And I think that that kind of misses something. I don't think you can reduce intelligence to HTTP GET, right? What they mean is labels. They mean answers, right? It's kind of marketing, blah, blah, blah. And we found that at the Zooniverse, we're kind of privileged in the problem we work on. It's interesting, people care, they talk about it, there's kind of a curiosity to it. And we found that our best discoveries don't come from the labels that people give us, they've come from people talking about what they see in the data. Because they've, at this point, looked at more galaxies than I have. Even that guy, you remember? He's seen more galaxies than me, and I'm an astrophysics PhD student at Oxford. Right? So maybe, if he'd actually paid attention to them anyway, that's a question, maybe he'd be able to tell me something about something he'd seen. People have discovered planets. There's a planet around, the first planet ever discovered to be in a double binary system, so two stars, planet in the same solar system, was discovered by people chatting on our forum about data that they'd seen. There's a huge ionized cloud of gas in a galaxy that was discovered by somebody who's being like, hey, what is this weird green smudge? And it turned out the green smudge was hot oxygen being ionized by the radiation coming out of the sort of supermassive black hole in the center of the galaxy. As it beams through, it ionizes this pocket of oxygen, and we can see it in our image. And it turns out that's kind of common. We found 20 of them now. So this person discovered a whole new kind of astronomical object just by having somewhere to talk about it and looking at a stupid number of galaxies. So I don't think we should phrase it like this. I think we should try and keep the humans able to feed back to us, the modelers. And if it's not quite that dramatic, you guys know the importance of being close to your data when you're trying to construct features, when you're trying to interpret what you find, or you're trying to communicate that. And the humans in your system might know more about that than you think. So even if you're not doing a science project, not doing something that people are naturally happy to chat about, you should think about building a structure where people can talk about that, where they have an incentive to do so, where you reward people for giving you good insights. And I think that that would be better for us as modelers and better for them. So that's kind of my suggestion. Science is not quite the same as data science. We find it really hard to be agile. For example, you want to run an experiment for a while. You don't want to change things fast, right? Every time you change something, you make your life 10 times harder because you have to compensate for it later. And then suddenly you're stuck in a data analysis for the next 6 years. You never write your thesis, and I'm totally not worried about this at all. But I think that we have a lot to learn from you guys in terms of building models. And I hope that this presentation has communicated something that at least makes you guys interested in data science for science. And if you want to chat more about that, come find me. Thanks very much for your time. Any questions? Yeah?
So, I'm not really up to date on the sort of human in the loop systems, but Cloudflower used to be kind of quite entitled advice about the way the doing things. Does this platform already incorporate a lot of the work they've done?
Well, it's hard to say. I mean, I think they're rebranded now, Figure 8, so don't hurt me, Crowdflower lawyers.
Okay.
So they don't really tell us what they do, because what they do to be smart about aggregating the labels of different people is their commercial edge. And I'm sure Mechanical Turk and the other services do the same. So the only reason I can talk about this is that we're not making money. So I find it really hard to compare, because they don't publish papers about what they do. I know who listens to like Twimmel Talk in the room, the podcast. They've had a few episodes of Figure 8 in the last few times. And I noticed that their scientist was kind of saying, yeah, there's a few papers starting to come out, but really we're at the cutting edge. And you really have no way of verifying what they're doing at all. So we're just going to have to trust them. So we'll find out. Yeah.
I have a friend who's a radiologist, and we often get talking about machine learning and radiology. I was wondering, how a lot of the stuff you're talking about there and getting feedback seem the same routes. Have you made any parallels with research that's going on in radiology?
I think in terms of the model building, there's a lot of parallels with medical imaging. We have quite complicated, messy images, potentially quite small numbers of them, and we want to infer something about it. That tends to get into medical imaging, and uncertainty, again, is something medical people are really concerned about. I'm not sure. I think what we'd like to do is, if you have a radiology problem, chuck it on the platform, and we'll see what we can build. So we're quite happy to fit to particular use cases if there's a genuine need, and especially if you have some science funding to share. So that's the pitch. Yeah.
Thanks for the talk. It was very interesting. So the method you suggested that basically relies on having a big amount of data. Does that wouldn't work if you have only a small data set, like we just had it with the medical imaging?
Yeah.
Will it be more or less likely?
Well, I did my master's project doing this for merging galaxies. I had 1,200 galaxies, of which 200 were merging. And people are kind of surprised. You can use CNNs for much smaller data sets than people typically think. And I think the reason is that all the like cutting edge press stuff, a lot of it is like ImageNet. You have millions of images. You have 130 layers, right? But you don't have to do that. If you have a simple like 3-layer CNN, one fully connected layer, you have some aggressive dropout. You have some very aggressive data augmentations. So if you know there are invariances, you can exploit them, like with Galaxies, if I flip, if I rotate, if I zoom in, crop, etc., that I should get the same answer. Maybe some domain-specific stuff, like adding Poisson noise for photon counts in the detector. Then it turns out these methods actually work, pretty well. Think about the like hot dog, not hot dog app, for example, right? How many hot dogs do you think they took pictures of to do that? Probably not that many. I love that I can cite that, by the way. Yeah.
You said that the amount of galaxies that you are classifying at the moment and to the amount of galaxies that you need to classify there is quite a difference. Where do you think are your bottlenecks?
The bottleneck in terms of labeling is how many volunteers I have classifying on the site. So if you have kids, just saying, there's just only so much you can ask people to do, and only so many people using it. And realistically, I also want to be clear about it. Like, even if I could have, everyone in the world would spend 5 minutes a day on my website, maybe I wouldn't want to do that, right? If I could be smarter about it, maybe I should only show them the things that I really need to know about. So that's my bottleneck, really. It's not computational, it's just the amount of labels I can get. If I have good labels, hopefully I can make arbitrarily many predictions. Are there any women with questions? We haven't really had any female questions. Yeah, it's fine.
All right, sorry.
Yeah, it's okay.
Just a quick question. So when you actually get the distribution of your certainties, so to speak, how do you classify if that distribution is, or how do you exactly threshold that to say that, oh, this observation is more uncertain versus certain?
Yeah, it's a good question. I think it becomes a pure statistics problem, right? You have a distribution, you'd like to quantify your uncertainty in it around some, maximum likelihood estimate, say. So I think I kind of refer you to the statistics on that. And I think that I would, you do stuff like, if you have your likelihood estimate, you can estimate a confidence interval, and you can set your confidence interval to however much you like. And really, that's one way. Or you can talk about entropy and the amount of information in the distribution. That's another way. But that's kind of now outside of the sort of machine learning realm, I think, once you got to that. Maybe, yeah? Can we wrap up?
Yeah.
Okay. Thanks very much for your time, guys.